Next video is going to focus on precision and accuracy. Accuracy is assessing how close an experimental value is to a true value, how close you are to the target. We typically are able to quantify this with percent error by either using the value that has been measured experimentally or calculated using experimental data, or the average of a series of values that have a commonality to them, comparing that to the accepted value. We take the difference between the two. We are not concerned with whether it is higher or lower, so we take the absolute value, and we divide that answer by the true value to see how close we are to that target. This is basically another way of looking at how we determine what your scores are on assessments. So because we have to do the subtraction as well as the division, we want to make sure we follow order of operations and we take care of the numerator first, and then we divide by our denominator. When we're looking at precision, sorry, my mouse does not like me. You can look at it by your decimal places, how much information the measurement provides. You can also examine it, and this is how we typically do it with lab, by looking at reproducibility of our measurements. We want to make sure that we're getting consistency with our data. If we have a wide range of measurements for the same type of experiment, then we know that there are some issues with our precision. We need to take a look at that. We can also calculate precision or examine precision using deviation calculations. So here we have the mass and volume of water were measured by a student multiple times in lab, 3 times to be specific, and they were used to calculate its density. You were given what the experimental values were based on that data collected, 0.975, 0.990, and 0.955 grams per milliliter. And we are told at 25 degrees Celsius, remember temperature does play a role with your density values, that the accepted density of water is 0.998. So the first thing I ask you to do is to calculate your average experimental density. You won't ever have to show me how to calculate averages. Just as a review, we take all the measurements that we're wanting to average together, we combine them together by adding, and then we divide by the number of measurements. The number of measurements is not a significant value. It is not based on any sort of measuring device. It's a counted number. So when we are doing this particular calculation, we want to make sure that when we add the numbers in the numerator together, we keep the same number of decimal places as our measurement with the fewest, which would be 3. So I got 0.973333333. And then when I divide it by 3, I already did the divide by 3. I got 2.920 when I added them together because I wanted to keep that third decimal place. When I divide those values by 3, I want to keep the 3 sig figs that were present in the numerical quantity, and that gave me 0.973333. So it would end up at 0.973 grams per milliliters. When we are doing that addition, you would actually have a total of 4 sig figs because of the 2 in front of the decimal places, but the decimal places are what was determining our precision, and since we're dividing by an exact value, we want to keep that number of decimal places. For number 2, we're going to look at range. We're going to look at highest minus lowest. And so we look at our 3 measurements, 0.975, 0.990, and 0.955. And we take the difference between the highest and the lowest, so that would be 0.990 minus 0.955. And when we do that, we get a difference of 0.035. Both of the measurements had 3 decimal places, so our range needs to have 3 decimal places. And then we can calculate percent error by taking our average value, the 0.973, and taking that away from the accepted value, 0.998, and then dividing it by the true value, 0.998. We want to make sure we subtract first, and then we divide. So when I subtract 0.998 minus 0.973, I get a difference of 0.025, giving me my 3 decimal places. I divide that answer by 0.998. That is not an exact value. That is a measurement. I got 0.02505. So I want to keep at least, I want to keep 2 sig figs because I had 2 in the numerator and 3 in the denominator, so 0.025. Remember, with percent error, you need to make sure you multiply by 100. That 100 is an exact value. It will not affect your sig figs. So when I round it, it's going to be 2.5%. What does this really tell me about accuracy and precision? The smaller that percent error value is, the more accurate your data is. I typically say if you are under 10% error, you have fairly accurate data. If it is greater than 10%, your accuracy is not where you would like it to be. In terms of precision, we look at the range compared to our average value. What fraction of our range makes up our average value? So when I divide 0.035 by 0.973, and I turn that into a percentage, I get that that range is roughly 3.6% of my average value. That too is in that 10% threshold. So if my range is 10% of my average, if my percent error is under 10%, then I've had good precision and good accuracy. If I've gone over that 10% threshold, then my accuracy and precision is lacking.